Good evening and welcome everybody. My name is Obi-Wan Pez and this is N-Simplex Pachinko. We are doing some math tonight. We are on allegedly night 13. I think that's right. And want to welcome to the show. Tonight we have Zach at e to the 2i pi. If you would like to introduce yourself.
I think y'all know me, but I'm Zach. I'm here to help out with the course and just talk through differential equations. It's an area that I'm interested in and able to offer something about. So I'll do my best tonight.
As well, everybody should. No, yeah, we really appreciate both Zach and Ian Stuckey have come in and helped out with the course, both being people who have worked on differential equations for a long time here. Still coming in, exploring the space, if you will, to try and understand maybe some good ways of teaching, notes that anybody has for fixing my ways of teaching, because believe me, I need it, or anything else for that matter. So yeah, we also have Stuckey's going to be coming in just a minute.
All right. Any minute now.
There we go. Would you like to introduce yourself?
Sure. I'm Ian Stuckey, the host of The Mathematical Creature here on Twitch, as well as the organizer for No Royal Road, a geometry study project.
Awesome. Welcome on in, everybody. All right, so for the last couple of weeks, we have been working on matrix systems, which specifically have been dealing with... I wouldn't think that would happen so early. That is not what I wanted. My icons are all over the place. Okay, cool. So we've been looking at matrix systems, which have been looking at what would happen if we had some system, for instance, usually we call it XY. What is going on? Alrighty. I think we might have already crashed something, so that is awesome.
Draw crash already?
It appears to have. Zach, you also got super quiet.
Oh, I'm sorry. I can turn up my... There we go. That's better. The volume had just turned down.
Ah.
So I think we're okay now.
Yeah. So typically we let our x be either some combination xy. We could also let it be x1, x2, whatever we feel like to indicate that these are linearly independent vectors that we're going to be looking at. So in this particular case, again, we look at it as x prime is equal to, and what does that top row say?
You mean like the 1911, or like interpreting it? You mean?
The 1 and the 9, yep. Top row.
Yeah, so 1 and 9. I guess I was missing the trajectory of that question.
Yep, that's fine. So if we wanted to split up our two equations, what would they be?
So you might write it as 1, 1x and 9, 1y. So you have the vector 1, 1x, 9, 1y, right?
Sure. So we can make this capital.
I mean, I guess I don't know in what spirit we want to do this. So we have the 1, 9, 1, 1, and then you're multiplying that by xy, or x1, x2, as you like.
All right, just 1 second. Let me check my system and see what crazy stuff is running in the background. Because this does not appear to be happy with me right now. Firefox appears to be taking up 100+% of my CPU, so maybe we will...
Ouch, yeah. That's not good.
I'm going to quit all Windows just for a second and hop right back in. There's also an isolate... What is that? Isolate webco. That's probably a sub part of this. I don't know what's... Oh dear. Okay, we will instigate sigterm. Okay, so sorry about this, everybody. Probably should have restarted before stream, but you know, some things you just forget. Okay. I appear to be back. Although, is anything that I wrote still here?
So I wasn't seeing it when
maybe
on
that's
the first go around.
That actually makes complete sense as to why I was just talking. Apparently nobody was seeing anything. All right. Awesome. Technology, everybody.
I was gonna say, it's always great when technology works, and when it doesn't, you know. I've been there.
Oh yeah.
Okay, so there we go. So we have our system here, x prime is equal to 1911 times x. X is again a vector matrix, and x has been labeled either as xy or x1, x2. Are we seeing it now?
Yeah.
Excellent. Yeah, so my initial thought was to do lowercase x prime is equal to, and then what does that get us for this particular system?
X plus 9y.
All right, and y prime is equal to?
X plus y.
Okay, so if we leave this here, obviously, right, we get the same matrix system that we were talking about before. We could do our solutions, trying to find our null space solution. In this case, that's all that there's going to be. There is no non-homogeneous portion, so we don't have to worry about that. And we want to get our eigenvalues and eigenvectors, which would then tell us what the null space is going to be. Or a null space solution. But there is also something that we can do here. And we can get everything in terms of one of our variables. Now, take your pick as to which one you like, but I'd probably prefer manipulating the lower one because all of the coefficients are 1. Makes it a bit nicer, no fractions involved, all that good stuff. So if we wanted to solve for one of the variables out of the second equation, I would probably be more prone to solving for x than attempting to solve for y. So in doing this, we could say that we have x is equal to y prime minus y. And then taking that in concert with our first equation, we can now have this be parentheses y prime minus y, all prime, is equal to y prime minus y plus 9y. Now, what if we just... Go ahead, Zach.
No, Obi, I was gonna say I'm watching your stream. I can't see what you're doing.
Oh, Yes, that's
So it
because
might be
I
good
closed
to,
the window.
like, as you're talking, I'm sort of not able to.
No,
I
it's
didn't
because
know
I
if that was
closed
just
the window.
me or not. Yeah.
All right, that should do it.
Okay.
Thank you.
Yeah, there we are.
Definitely needed because yeah.
I'm watching what you're doing, and I'm thinking like, I was trying to figure out like where you are, and I was just losing it a little bit. So
Yeah.
okay, we're good.
Thank you. This is the opposite problem that we were just having. Okay. So now that we have all of this, this is our new differential equation. What is it? And
Well, it's.
Good.
Do you want to finish? I didn't want
Nope.
to steal your thunder. Okay, so I'm looking at that, and I'm seeing that there's a derivative of of a function and its derivative. So we just use the rules of calculus and say, well, that's y double prime minus y prime, right? And then we get a y prime minus y plus 9y.
Right.
And then we can bring stuff together, right? Like you can just y double prime minus 2y prime minus 8y equals 0.
Yep. So based on this, we now have a differential equation. And how do we classify this?
Well, it has a second derivative in it, so we might call that a second order differential equation.
Mm-hmm.
And it's ordinary. It's homogeneous. And linear. Is there a rule to the, like, you know how adjectives follow a rule in English, and you're supposed to, like, there's the I forget what it's called, but there's an order to it. Is there an order to ODEs? I actually have never seen an official order that I know of, but I'm sort of curious.
I don't think that there is necessarily an order, but I think it is in terms of specificity and like what tools are going to help you the most in each case. So by separating ordinary and partial differential equations, that's like a massive burden that's been lifted off. Because then you're saying, okay, if it's an ordinary differential equation, we have an entire suite of things that we're doing here in, as a part of this class, which is going to tell us that we don't need partial derivatives or partial integration or any of that stuff. So I would say that is essentially partitioning our problems into the two largest pieces. So ordinary and partial differential equations. Then when we go down, we know that first order differential equations have been the ones that we've been looking at the entire rest of the class. So we've just been really talking about first order this entire time. We did have first order systems, which now we're also seeing a first order system can be equivalent to a second order differential equation in this line. And again, I think mostly that kind of partitions one of the biggest chunks of the ordinary differential equations off again. And then when we start talking about, well, if it's linear or nonlinear, then we have two, again, very different strategies to go about. And then homogeneous is sort of an afterthought because it's such a small part of the differential equations we've looked at so far. If it's a first order linear equation, it doesn't matter if it's homogeneous or not. You're just going to get an integral of this function that you had over on the right. And if it was a first order system, then yeah, we're going to have this extra term stuck on the end, but we did a bunch of stuff that we said first of all we wanted to find the null space solution. Then when we were done with that, then we look at to try to find the non-homogeneous portion, non-homogeneous solution.
Yeah,
So
that seems reasonable.
yeah, so I don't think it's a necessarily like hard and fast rule, but at the same time, I think this would make it most convenient, because if you start talking about second-order homogeneous differential equations, an expert might be like, okay, hang on, is that ordinary or is it partial? Because that's really important to know.
Well, and that really is. I'll speak from a somewhat of a, a novice expert, I feel. But as far as like seeing the difference, there's absolutely that's important to see the difference, to see that that's there. And it's actually one reason. I don't know if you're going to talk about partial differential equations at all, but the notation I use, it tends to be more explicit. So I tend to write dx dt instead of and partial x partial t instead of x sub t or whatever, or x dot or all of that.
Yep.
Just because it can get ambiguous.
Yeah, definitely. So the subscripts are a potentially convenient way to do partial derivatives, but again, as you said, once you start getting into it much more deeply, you start appreciating really good notation. I certainly did when I was doing partial, as part of my... Man, that's big. When I was doing partial as part of my master's. All right. So we have an ordinary second-order linear homogeneous differential equation, and now we say, okay, what are we going to do with this? So, in a very similar way to how we looked at our null space solutions in first-order systems, we also want to kind of go about the same route that we did with that here for second-order differential equations. Now we could back this off and say, hey, let's go find another... let's go find a system that's going to work for us and then break it up into a first-order system and find all of our eigenvalues, eigenvectors, etc. However, in this particular case, that's backtracking. And if we end up just with a second-order system like this, with no other context, some people might feel intimidated by first-order systems. Some people have not studied it by this point in their course. And a lot of, again, I'm doing this sort of backwards to how a lot of classes typically teach it. So most of the time they say, all right, what we're going to do is we're going to take sort of an informed guess. I know Zach kind of railed against this at one point, but in this particular case, we could say, okay, based on all of our experience with our null space solutions with first order systems, what kinds of functions did we get for our null space solution?
We got exponentials, sometimes t times exponentials, and sine and cosine, which were secretly exponentials. So I'm going to go with that.
Right, so our solutions from first order systems looked something like y equals c1 times our eigenvector c1 times e to the lambda 1, our first eigenvalue, t, plus c2 times C2 times e to the lambda 2t. Okay, so that's what our solutions typically look like. And then we want to discuss real quick, again, then our solutions for second order differential equations likely are going to look at least similar. Okay. Still here. So we should get something similar. Now, in this particular case, there is no eigenvector. There's no need to create a system. So we're going to say that our y should probably be an exponential function of some kind. And then we're going to say that we had an eigenvalue for this particular thing, lambda times t. And it should look something like this. We're not entirely sure what it's going to look like, at least from this perspective, but again, something similar to this. So if we were to let let our y be this particular thing, and then we say we know, you know what, hang on, let's go back and get, we're going to need our y prime and our y double prime in order to make all this work. So what is y prime?
E times lambda e to lambda t.
It would have another lambda on it, essentially. Yeah.
Right, so our constant is going to get knocked down front. So c times lambda times e to the lambda t. And then y double prime.
Same thing, but you're going to have a lambda squared. Instead of a
Right,
lambda.
c lambda squared e to the lambda t. Okay. So now we go back to our original equation, or the second order differential equation that we created, which was y double prime minus 2y prime minus 8y is equal to 0. Is that correct?
That's it.
Okay. Get all those, and we plug all of them into this, and what do we get?
Let's see here. So, well, c is going to stay. You get lambda squared e to the lambda t minus 2c lambda e to the lambda t and minus 8c e to the lambda t.
Is then equal to 0.
Yep.
Okay, so what is this helping us find?
Well, we want to know what lambda is, right? E to the lambda t is a common factor. So if we were to solve this algebraically, we might say that, and those are the eigenvalues, yeah, because that's what we determined previously. But I mean, you can look at the whole equation you've written, and we try to figure out what value of C allows the and what value of lambda will give us the equation above. Like try and match coefficients in essence.
Okay, so what does C do for us?
I mean, in a way, isn't that like there's an eigenvalue, and then you have a constant, which is usually connected to your initial conditions.
Yep. And in this particular equation, what's happening?
So I'm noticing that the C value, just by inspection, if I look at the y term and the y prime term, it would be convenient to make the C equal to 1, and that lambda should also equal 1. And by doing that, I should get everything, this equation matches.
Well, we can't necessarily say that lambda is going to be 1.
True. But
because again, that's our eigenvalue, so we're kind of trying to find that. We don't know what its value is going to be. You could make some suppositions, but
yeah, I mean, I'm making some inference here. Just like my intuition tells me a 1 is going to be one of the eigenvalues.
Okay,
so I may or may not know that.
So if we're going to be setting something equal to 0, what's a good strategy that we're trying to do?
Well, I mean, e to the lambda t is a common factor, right? So we could factor this, and we know that if we choose c equals 1, then we can solve for lambda maybe.
Okay, or what would happen with c alternatively?
Hang out with the exponential.
Yeah.
Yeah, that's true too.
So c is just getting, or can be, just pulled out with all the rest of it, or you can let c be 1 for kind of an arbitrary case in this particular moment. So what's left?
Lambda squared from the first term, 2 lambda from the second term, and a negative 8.
Yep. And if all of this stuff is equal to 0, what does that have to mean?
One of those factors is 0.
Right? And how do you feel about e to the lambda t?
Ooh. Not 0.
Right? So this term is never 0.
As exponentials.
Right? At least in all of our experience that we've had up to this point, we don't want to consider the idea that e to the constant times t is going to be a 0. So it happens at negative infinity, but we're not going to deal with that. How do you feel about c? I mean, earlier Zach said just let c be 1 and we can kind of be done with it for the moment.
Yeah. Well, I mean, c really, if c were 0, that sort of is possible, but that would be sort of silly. I don't know if that's really all that helpful.
Right. So typically we call that the trivial case, and we just say yes, of course, c could be 0, but c could be 0 for all differential equations, so it doesn't really matter what is on the board right now. So we can always say c is, all of our c's are always equal to 0, and we'll always end up getting 0 at the end. But again, it's just sort of silly, so we just go, okay, whatever. Sorry, were you going to say something else?
No, I'm good.
Okay. Okay, so this bit right here is what's called our characteristic. or characteristic equation. This is the bit that gives our differential equation its character, to tell what kind of differential equation, what kind of solution do we actually have here. And this is the same thing that we saw with the eigenvalues in first-order systems, because these are eigenvalues. They are exactly the same thing. So in this case, our nullspace solution ends up with lambda squared minus 2 lambda minus 8 equals 0 as our characteristic. And then what are the solutions to that one? Or what's the factored form if you prefer?
Lambda minus 4 and lambda plus 2. I was wrong. Lambda was not 1. Yeah, I was a guess, but I was wrong.
Yep.
I've been wrong before.
And it certainly won't be the last time for any of us. So
I was gonna say, yeah, there's no. That's certainly the way it goes. Yeah, lambda 4. So 4 and minus 2 are eigenvalues.
And does it make sense that we have 2 eigenvalues?
Well, we had. Yeah, I was gonna say we do. We had a system of 2 equations, and so yeah, as long as the columns were linearly independent, which they are, and as long as I think we should be okay. It's a full rank matrix. That's what I like to call it.
So what we're going to see is that the order of our differential equation is going to match the number of variables in the first order system, which also then matches the number of eigenvalues. Math. Close. And that'll match the number of eigenvalues in both of them. So again, the order that we have in our characteristic has to be the same as the number of variables in the first order system, which has to be the same as the number of eigenvalues that we have. Now, keeping in mind, again, some of the eigenvalues can be doubled. You know, we could have matching eigenvalues, so it could require that we change our system a little bit, or change our possible solution a little bit in the end. It's all the same sorts of behaviors that we saw in first order systems. It's just now being reflected into, single line, higher order differential equations. Right. Any comments on that?
No.
Okay.
I'm good.
So with lambda being -2, +4, means that our solution is going to be y equals. How do we manage to write this one out?
So we're going to have a constant with an e to the -2t, and then another constant with e to the 4t.
Okay, and why do we have to have those constants there?
Well, initial conditions. There could be there's multiple. This is a family of solutions that can occur, just like we had in systems. There's a whole family of things that could happen, and so we need to account for that based on usually a function, the initial value at the function and the initial value at its derivative. Usually how it's given, but
okay. Somebody want to try plugging this into the differential equation? Or you can divide and conquer.
Whatever. Let me see.
There it is. Okay, so
Hey, Pen.
this is
Good evening and
good.
welcome.
Oh, hello, Pen Center. We want 8 of those. Minus 8 of those. Minus 2 of those. 1 of those.
I am optimistic that's going to check out. I'm seeing the 16 minus 8 minus 8 for C2 terms. That will check out. And then I'm seeing a 4 plus a 4 and then a minus 8, which again will give us 0, which is exactly what we'd expect.
And Stucky, the first one, I believe, is a -2 times -2.
2 times -2. Yeah, okay.
I would definitely.
Excuse me, I need to step out for just a little bit. I'll
Yep.
be back. I'm going to put myself on mute if
One
you don't
one
hear
last
from
little
me
thing
for
there,
about-
Zach. I would definitely buy
Yeah.
those T-shirts. So.
Yeah, I was gonna say. Like I was thinking, it's solely Pen Center's idea, but I think it'd be a great one. We gotta come up with some like cool marketing for that. That could be a thing. All right, I'll see you in about 30 minutes or so.
Sounds good.
Yep.
Right.
Okay, so we've proven that in this case, it doesn't even matter what C1 and C2 are as long as they're real numbers. We're going to get 0 for this entire thing. And technically, I guess we could say, yeah, they could even be complex, but we're not going to go there. That's Pen Center's job. So we end up getting 0 here no matter what the constants are. And so this feeds into what we were talking about earlier. This is our null space solution. Or homogeneous solution. And if we look at it in terms of each one of them separately, we could have, yet again, looked at this and said, well, either of them could have been the sole solution to our differential equation as well. So in this way, we could have had y equals c e to the -2t, and we could have had, y1 being that, and y2 being c e to the 4t. It's only that we bring them together because we want the most complete solution to this particular, I gotta stop using the word particular, to this differential equation. So the entire null space solution is getting us our 2 linearly independent vectors. It's making sure that we have the appropriate number of eigenvalues and appropriate number of terms in the null space. Again, the most complete solution. This is also called the principle of superposition. Which allows us to say that if y1 and y2 are solutions to the same differential equation, then a linear combination of those solutions is itself also a solution. And in fact, it doesn't even matter what order we're talking about. So we could have said y1, y2, dot, dot, dot to y sub n. Any amount of these that we want to talk about. Same principle of superposition is going to hold. Now, we saw that that was true in this case, but we could also... we could show that it generally holds, but I think that most people would probably agree that as long as it's working in all of the cases that we see, that, you know, you all can go find a proof if you're really desperate for it. We don't need to do that here. What do you think, Stokey? Agree?
Fair enough.
Okay. So this is our y, which was also, if we go back a bit, this is also the y that is our y solution to the very top equation. So if we went all the way back to the beginning of this problem and looked at the differential equation that we had, our x vector prime is equal to, what was it, 1911 times the x vector. This is our y solution. So now we'd also probably want to go back and say, okay, what was our x solution then, given this y solution? How would we figure that one out?
Well, the first thing we did was we said x is equal to y prime minus y. So we can plug in there.
All right, what's y prime? Oh, you already wrote that up there, yeah. All right.
And then subtract y.
Right. I'm okay, I promise.
Okay.
Okay, so then x is going to be equal to?
Minus 3 in front of that. And plus 3 in front of that.
Which now means we have a solution to the first order system as well. So if we were to go back and if we wanted to do this in terms of the first order system, I'd recommend to any students that are out there, you want to give your answer in the same form that the original problem was stated. So if this was just solve the second order system of, or solve the second order differential equation, y, where is it? Y double prime minus 2y prime minus
x is equal to yeah. So we get four from the top term, 3 lambda, oops, and then lambda squared. And we can factor this, maybe. Not well, but
we may have problems.
This is equal to 0. And so lambda is -3. 9 minus 16. 2, 4 AC. Looks good.
That's a little gross. How'd that happen?
Well, that's a little gross.
Well, it's not the same one in my notes, which is a little strange, but I think I just, like, made up a new problem instead of following through with what I was doing. I don't know. That's weird.
Yeah, just making sure that I got the coefficients doing the right things. But I think I'm happy with that, yeah.
I do see one small thing. Nope, never mind. You got it. I wasn't shifted over far enough. Yeah, so there's, in this case, we're going to have non-real complex. And what did that do for us when we were in first order systems?
We got some sines and some cosines.
Mm-hmm. And so in this case, we can just, like, jump to the yes, I know what this is going to be part, if you would like. Since we already did the work on first order systems in terms of trying to get, I left a slide in, oh gosh, it was like a month ago. When we got to first order systems, we had one that was like this, and I did the workout off stream because it was maybe going to take a little bit of time to convince some people if they didn't have the familiarity with it. So in this case, right, we're going to get C1 e to the, what's it going to look like?
We're going to start with the exponentials form?
We're going to just jump to the end and say, like, what does this look like with the sines and cosines in place?
Okay, I see. So
if you're comfortable with it.
Yeah.
Yeah.
3 halves, right? Times root 7 half, root 7 over 2, or times t, and sine of that, sure.
All right, then.
And the same thing, but C1 is C2, sine is cosine.
Right. So this becomes a little bit, or this is just the exact same thing as what happens with the first order systems, yet again. The thing that might throw some people off again is like, why isn't there an I term in with our sine? Because it usually should be I sine. I can't remember if you were there that night or if you just happen to know that one offhand, but
I mean, yeah, so you can say this as in the I is absorbed into the C1.
right, so the way that we did it, one explanation, right? Explanation 1, I is absorbed because it's a constant. Right, there's pretty much no fanfare about that one. It's just a constant, so it gets absorbed. No big deal. Explanation 2. Excuse me a minute. Sorry about that.
All good?
So explanation 2 is more or less along the same lines, but we're going to say that the fundamental set of solutions is x1 in this case e to the negative 3/2 t times the sine of root 7/2 t, and x2 is going to be e to the negative 3/2 t cosine of root 7/2 t. So the fundamental set of solutions doesn't include the constants, and we also worked that out in the proof part of it. And then the part that we did in the first order systems was that we said, okay, well, since we have the fundamental set of solutions, then x, our total solution of everything, is going to be c1 x1 plus c2 x2, just a linear combination of those things. So either explanation works just fine. It basically comes down to the same thing. I is just a constant. It's not going to be included in either the fundamental set of solutions or in the total solution up top, just because, again, we absorb it into C1, it's a constant, it's still going to be a constant after it absorbs an I. Alrighty. So in this particular case, if we wanted to say, if we wanted to generalize our solutions for this, if we get lambda is equal to a plus or minus bi, then we end up with the solution x equals c1 e to the at times sine of bt plus c2 e to the at, still at, cosine of bt. So this becomes a nice generalization that we can use for second-order differential equations. And also, this does actually work if we just use the above eigenvalues. So if we used -2 and +4, we could plug that into here as well and get exactly the same thing.
What?
So if we went through okay, fun times. So I apparently expanded this out further than I thought I did. Okay. So the problem is that I just jumped to the end and we wouldn't be able to plug it in here. We would be able to plug it in back a ways. So apologies. If we'd said that our x solution was going to be c1 e to the lambda t lambda 1 t plus c2 e to the lambda 2t and then separated all this stuff out as a plus or minus bi, then we would have multiple different terms. So if we still let our lambda set be equal to -2, +4, but translate them to -2 plus 0i and 4, come on now, plus 0i. This might be too far afield.
Because the sine term is just gonna vanish.
Right. So in each of these cases, we end up with our -2t times e to the 0i, and in this, the e to the 0i becomes both the cosine of 0t plus I sine 0t. Hey, Zach.
I'm back.
Hey, welcome back.
Thank you. Looks like we're in an ad break anyway.
Oh.
Although that might be because I'm...
Yeah, that's just
gonna
because you
reload
came
the
back.
Window.
Yep.
Yeah. Okay. All right, we're good.
Okay. So, the point here was just that this was going to expand out as a much larger system, and then, yeah, our sines drop out, our cosines stick around, and we still end up with the same structure overall. It is a bit different just because, again, I can't jump to the very end and say, oh, look, if we just plug this in, it'll be fine. So because there are two separate eigenvalues, we would have to have a separate linear combination for each of them. So a plus bi would be one system, and a minus bi would be another system. Sorry, linear combination. Let's not use the word system there. So again, this would be a little bit silly, but in theory we could still do it. Okay. Now, I did use a phrase up here that you didn't push back on at all. So somebody might be like, hey, wait a minute, you used that word. When we're talking differential equations, we talk fundamental sets. What's like the major concept that we used in order to check whether something was a fundamental set of solutions?
Typically linear independence, right? You're checking for whether these two things are different in some sense.
Mm-hmm. And when we had first order systems, what was the check that we had to see whether a system was going to be linearly independent? Because we used something in particular.
The Wronskian?
Yeah. So when we use the Wronskian matrix, this was trying to make sure that we had that linear independence. In this particular case, we don't quite have the exact same setup. Right? We don't have eigenvalues and eigenvectors. We just have eigenvalues. And then we want to know if the rest of the stuff makes a fundamental set of solutions. So for second order differential equations, we have something that is similar to the Wronskian, or it still is called the Wronskian, but we don't just fill it with, x1, x11, x12, x21, and x22. In this case, what we do is we say, okay, our first solution, x1, is still going to go in at the top, and x2 is going to go next to it. But that's kind of it. So here, we did relate, up in the first area, the derivatives of each of these things to each other. In the case of the Wronskian, we should then be able to say, well, if this comes out with a singular value, i.e. that the determinant of this matrix is equal to 0, then we're going to have something that must be linearly dependent. I think my shortcut was that we said, really what we're looking to see is whether these functions are of different types than each other, or if they just end up boiling down to being the same type of function. And I don't mean necessarily like, oh no, they're both exponential. So the issue ends up being, are they the same, are they exactly the same type of function that is then going to cause them to not be linearly independent? So in this case, we're saying we want the product x1, x2 prime subtracted by x1 prime x2 to not be equal to 0. Because again, we're saying that this is going to prove linear independence. All right. Comments, questions?
Not right now.
Seems okay.
All right, so if we check our set of solutions that we had associated with, you know what, let's do a different color there. We had our set of solutions associated with these eigenvalues. Again, x was going to be equal to c1 e to the negative 2t plus c2 e to the 4t. We would want to look at, again, what are the fundamental portions? So in this case, just the e to the negative 2t and the e to the 4t. Put that in our Wronskian. E to the negative 2t, e to the 4t. Negative 2, e to the negative 2t, 4 e to the 4t. All right, what do we get here for the determinant?
Uh, 4 times e to the positive 2t minus negative 2 e to the positive 2t.
Which is?
Looks like 6 e to the 2t.
Which is?
Not 0.
Right. Now, as a reminder, we could have something that is occasionally equal to 0. So if this ended up being like sine of t as our final Wronskian, we're not just looking for what individual values of t are going to cause problems for this. What we're really concerned with is the Wronskian equivalent to 0? So if we ended up with, for instance, sine of t as our Wronskian, that still shows linear independence. We're okay with that because it is not equivalent to 0 always. All right. Questions?
Seems good.
What's your favorite Pokemon? Gotta ask. You asked for questions, so I'm gonna give you one.
You know, it has been 20 plus years since I tried playing Pokemon Red.
Okay.
So I don't even know. I seem to remember just absolutely loving Mewtwo, but the problem was that it would kill everything so fast. You couldn't actually catch any more after you had like after you put him on primary.
Oh, yeah. That is difficult. It's a good choice, though. A little OP, but a good choice.
You, Zach, any preferences?
Not terribly. I mean, I liked more the idea of Pokemon Yellow, so I was more like Pikachu fan. But then again, I watched the anime.
Yep.
The anime. Gotta say anime. It's Japanese. Anyway.
Oops. Let me just double. Okay. Yeah. That's really the next thing. Okay. Okay. I thought I had another example here, and it just jumped up to something completely different. So I would much prefer apologies. Oh, that is not the book I thought it was. That's partial. There we go. Here's my notes. All right, here we go. Really, this is the one that I was thinking in my head just as you were doing the last one, Stucky. And this time I'm going to include initial conditions for us. Alrighty. So x double prime plus 4x prime plus 4x is going to be equal to 0. And the initial conditions are that at time 0, we're going to assume that this is time, x is 1, and x prime is also 1. So what do we do with this?
Let's get a characteristic equation. The x is the e lambda t.
I think we'll skip that.
Then, yeah. We're gonna get lambda squared, 4 lambda. That's the lambda, I promise. Plus 4 times an exponential, which will cancel. And that does factor. So, following on with our systems analogy, we that x is going to be c to the 2t plus, we'll give that a subscript and a minus sign. We could check that. Well, if that's what we want to do right now, but
Sure, I'd probably encourage that to be plus just because. Not that it really matters anyway, it's just a constant, but... Yep, so I would probably... well, yes, we can double check using the Wronskian to make sure that we have the fundamental set of solutions, or we have a fundamental set of solutions by doing e to the negative 2t te to the negative 2t, and then doing negative 2e to the negative 2t, and then here we have product rules, so this has got to be e to the negative 2t plus, nope, minus 2. E to the negative 2t. Which is going to end up being e to the negative 4t minus 2t e to the negative 4t minus parentheses. This product is going to be also negative, so that's going to get us a positive overall. T e 2t? Yep. 2t e to the negative 4t. Which these terms will end up becoming 0 when you add them together, but this one sticks around. So we get an e to the negative 4t, which is going to tell us that at least this is going to be a fundamental set of solutions, provided that we're correct in our assessment that plugging this stuff in will end up getting us 0 in the original statement. So if nobody's ever done it before, I highly recommend trying that out and plugging that in. Since we have both derivatives here, this is easy enough to work with. It's going to be right, x double prime is going to be 4c1e to the negative 2t plus c2 times the quantity. This is going to be negative 2e to the negative 2t, negative 2e to the negative 2t, and plus 4te to the negative 2t. And in that particular linear combination, again, getting 4 for first derivative and no derivative.
yeah, I'm seeing a 4 minus 8 plus 4 at the start. And then the minus 2t.
Right, this is where it gets a little complicated, but it's okay.
Annoying, yeah, but so
Oops,
4 from the middle.
Ends there.
I think we get our 0 there, right? The 4 plus 4 minus 8.
Yeah.
And then the others, well, the t e to the minus 2t terms, you get that with so 4 minus 8 plus 4, that's going to give you 0. And then the e to the 2t terms, or e to the minus 2t terms, you're going to have a 2 minus 2 is minus 4. Then you have a plus 4 on the C2 part, and that will give you 0 as well. So you should be, that should be clear. At least clear to 0, right?
Yep. So this linear combination of the derivatives that we had in that particular order is getting us 0 for all this stuff. So therefore, this is part of our null space solution, and therefore that's going to be our that's going to be the null space solution. Okay, looking good. Then
so we've got our general solution. We've confirmed that these are linearly independent, which is great. Do we want to solve for C1, C2? Or do we have enough information for that?
Looks like it. Yeah, so when x is 0, then we're going to get C1 e to the 0 plus C2 times 0 e to the 0.
So that means that C1 is equal to x0. Right?
Yeah, I see that. And x0 is equal to 1. That's nice. Okay, and then earlier we computed x prime there, so we'll steal that. For minus 2 C1 0 plus E2 times e to the 0 minus 2 times 0 e to the 0. That's 1 from the initial condition. Minus 2 times 1, since we know that C1 is 1 from before, plus that's 0, e to the 0 is 1, so it's just C2. A total of C2 is 3. No, that's wrong. Minus 1.
why?
No, it's 3. And put it back in. C1 is 1, so we'll it. C2 is 3. Oh. I think there should be some minus signs here. Right.
All right. Looking good. Any other comments?
Pepper jack cheese is really good.
Agreed. I didn't see any at the store. I'm just thinking, like, do we actually have that here? I gotta tell you, we can get about 10 different kinds of cheddar.
That's awesome. That's
All right.
wonderful. By the way, can anyone hear anything in the background
Music?
or anything? Like,
No.
that's good to know. That's really good, actually. So, I just wanted to know if there was annoying noise in the background, but there isn't. Okay.
Kids running around?
No, actually, that's not what I was worried about.
Okay.
So, but I won't mention it if you don't hear it. Then,
No.
then
Fine by
I'll
me.
be fine. Okay.
Okay. So now let's also do one other slight amendment to this, and if we end up with x double prime plus 4x prime plus 4x is equal to 10t minus 3 with the same initial conditions. Alright, so what's different about this?
Well, so this mirrors the same pattern we saw with the first order systems, in that we had a right hand side that was non-zero, or there was a non-homogeneous term, which amounts to having a function of t in here.
Yep. I gotta tell you, I almost put 10x minus 3.
Yeah, which would still be non-homogeneous, but
True.
but only barely.
Yeah, but it would also ruin the point of this problem.
That's true. That's true.
Okay, so in this case, what do we do in order to find our overall solution x?
In the same spirit, I think we're going to want to do. We'll find our homogeneous solution, which we know, I believe, and then we can now solve for a particular. So, which in this case, since we have something linear, I mean, we could do this in a number of ways. We could use the variation of parameters method. We could have inspired guessing. We could, we've learned a few different methods for that, I think. Is this Family Feud? So I have to get this at number 2.
Yeah. I bet you know it. Survey says.
Well, let's see here. You wouldn't call that method of undetermined coefficients, because that's number 1.
Right.
Let's see what other things we got there. It'll come to me. The strike's gonna come get me because I didn't get it in time. That's what's gonna happen. I was gonna say. Gosh, what's the other one?
So what are we working with here?
Well, it's a second order linear
Mhm.
thing. you could reduce the order.
Hey.
That's the one. There. I was gonna get there eventually. All right. Yeah, reduction of order. There it is.
Right. So these are the three major solution methods that we typically use with second-order differential equations that are just basically like algebraic methods. So if we just want to worry about getting an algebraic solution that is a closed form that gets us the most accurate, the most precise answer that we can get, we're going to do one of these three. And we're going to try to do undetermined coefficients if it's something that's kind of nice. We're going to do reduction of order if we, for instance, have a higher order differential equation that we would like to just solve a first order. There are particular reasons, to use each of these, but generally speaking, any of them are usually going to work as long as we follow some rules. So we'll see how that goes in just a bit. We did talk about undetermined coefficients when we were doing first order systems as well. So typically if you see something like a tangent, you're not going to be doing undetermined coefficients because we don't actually have a nice original function plus derivatives that are going to get us a fundamental set, unlike sine and cosine, which make a fundamental set by themselves. So reduction of order, variation of parameters, we're going to see each of those in turn doing some heavy lifting, if you will. So we'll get to those. We'll get to each of them in turn. So for now, what do we have for our homogeneous solution?
I think we previously got that from before, right? So it should be what Stucky got from our original solution. What was it? E to the minus 2t. I don't remember what the constants were, but they're there. Just copy and paste what we had before, I guess.
True. So an interesting question might be, is that going to suffice? Yep. Is that going to suffice for our homogeneous solution in this case?
So, because the derivatives of this, when inserted into our differential equation, if I put in xh double prime xh or 4xh prime and x all in there,
Mm-hmm.
and I apply this function, then we already established that would be 0.
True.
So if I put in the same thing with xp and whatever, I need that to be equal to 10t minus 3. So I'm okay with that. I'm actually really okay with the idea of just saying, yeah, let's solve a particular solution and just add it on to our homogeneous, because we already know that when I apply the differential operator up there, and I don't know if we want to go there, but the differential operator x double prime plus 4x prime plus 4x to xh, I'm going to get 0. So just that's okay. Just take that function, add it to our particular, we should be okay.
Okay. Stucky, do you have any thoughts?
I don't know how annoyed we're gonna be by initial conditions. I mean, so the thing that has to be 1 when t is equal to 0 is xh plus xp.
Mm-hmm.
And I don't know if we can just guarantee that xp of 0 is going to be 0.
Oh, I see. So you're saying because this wasn't an x0 equals 0 case, that this wasn't like that the 1 is going to throw things off?
Yeah.
Okay. I see your concern there. Because we knew that x0 or xh at 0, when we substitute, that gave us 1.
Right.
So that means that. So what I said assumed something. It assumed that we had x0 equals 0. And in our case, we need to then account for the 1. So that we just have to do a shift. Because we need the sum to be, in the end, 10t minus 3. I think.
So, very much right that all of this stuff, when we plug it into the differential equation, our x sub h is just going to get us 0, and therefore our 10t minus 3 is going to be essentially the leftover term for our particular. So we're going to find out, what are the coefficients that we're going to get for this thing, but where do we figure out x sub p?
I mean, by one of those methods we just talked about.
Right. And how do we then
Your favorite.
figure it out? With a linear function like this, what do you think my favorite is?
I would pick something linear and say that's going to be our particular, right? Like I just say, let's pick a generic linear function, at plus b, or if you want to be different, you could be, alpha t plus beta.
Yep.
Or if you really want to be different, Pac-Man t plus ghost. However you want to do it.
Yep. So we already said earlier that taking derivatives and multiplying by our coefficients, this is all linear operators. So we could separate out our x homogeneous terms, go filter them over here, our x particular terms over here, and then our x homogeneous terms, when we plug it into the differential equation, just gets 0 anyway. So that's all gone. And then when we plug x particular into our differential equation, we're going to get 10t minus 3. So here we say, again, what is x particular prime and x particular double prime? Prime's going to be?
A.
Woo! And double prime?
0.
0. This makes it nice and easy, at least for this one. Right, so our x particular double prime plus 4x particular prime plus 4x particular, again, has to be equal to 10t minus 3. And here we get a 0, here we get a 4a, and here we get a 4 parentheses at plus b. Okay, so now what?
Now it's just now solving for a and b.
Yep.
And you could have something like 4a equals 10, and I'm just taking the linear terms and relating those, and then 4a and 4b added together should give you minus 3.
So then this creates a nice little system of equations, right? Yep.
Right, yeah. I was going to say A is 5 halves. We know that.
B is minus 13 fourths.
right? Because this is going to end up being 10 plus 4b is negative 3, so 4b is negative 13, so b is negative 13 fourths.
Yep.
So, real quick, right? Did the initial conditions have anything to do with this solution?
No.
Not at all. Are these values of a and b going to be conducive to finding the initial conditions based on the numbers that we had earlier from our homogeneous solution?
No.
Right. So in this particular case, we could look at this and say, we can't actually guarantee that we're going to get 1 and 3 for C1 and C2 because...
You have to actually solve it separate, yeah.
Right. So these are essentially the offsets, right? C1 and C2 are going to be the offsets that we need in order to make our particular solution align with our initial conditions.
Right.
So we have
So
to
usually
redo...
you find this part. Yeah, you have to. I mean, all that will do is it will. The form though is fine. That's the thing. Is the C1 and C2 in principle when you apply the linear operator, that's still 0. So who cares, right? The relationship between C1 and C2 are going to be, you know, the specific numbers, I guess, are what are going to change.
Right.
But if you apply the linear operator to that solution, you're still going to get 0, no matter what. And then if you apply the linear operator to your particular, you get the 10t minus 3.
Yep. So it's really the
game.
derivatives where we get our 0 from the homogeneous, and then the contributing portion from the particular is going to get us that stuff over there. But that's all once it's been plugged into the differential equation.
You can tell how long it's been since I've solved one of these. Right? It's funny because I've taught this class before and I've done the same things. Like I feel like it's just been so long.
Yep.
Yeah, you get that. You know how that is.
Yep.
But
I'm doing the complete wrong one. Cool.
I mean, so far so good.
No, I did 4t.
Oh yeah.
Alright, this was t e to the negative 2t. Okay, so then that 4 goes away. It's going to be negative 2. Oh, come on. T. And also... plus C2e negative 2t. Right, plus 5 halves. Okay. And then double prime, we get our 4 C1 e to the negative 2t. We get a also 4 t C2e to the negative 2t. Minus 2 C2e negative 2t. And a negative, yeah, 2c2 negative 2t. And then we don't get a constant term.
Yeah.
Oh, I didn't need to do double prime. Right, because that was not the purpose of this. The purpose of this was to get our x and x prime such that we could input zeros in for t. Whoops. Right, so that's going to be C1 plus C2 minus 13/4. And that should be equal to 1.
Just
Stucky?
just C1. No C2.
Yes, thank you.
Yeah.
Right, because C2 is or C2 has a 0 attached to it. Okay, so C1 minus 13/4 is going to get us 1. Again, makes it nice and easy to solve. And then x prime at 0 is going to be, similarly, a bunch of stuff wipes out. So we get negative 2C1 plus C2 plus 5/2. Again, should be equal to 1. And again, gets us a nice, in this case, fairly easy system of equations. So C1 is going to be 17/4. Negative 34, negative 17/2. Just trying to make it hard on myself, it's fine. Plus C2 plus 5/2 is equal to 1. This is going to be a negative 12/2, so therefore a negative 6. And add that to both sides, we get 7. All right. Questions? Comments? Chair throwing?
Yar!
Usually something I ask my students if we come up with a potentially controversial solution.
I didn't know this turned into WWE that quickly. So.
Righto. There it is. All right, how we feel?
I'll take it.
You don't like it very much?
I don't like it very much. But...
It's probably fair. But as we said before, it really is just like C1 and C2 being different values here is trying to offset the fact that we have this other linear function which is kind of destabilizing our null space solution that we had before. So we have to reevaluate what the coefficients are for the null space solution in this, and here I can actually use the word correctly, particular case.
We'll play. We'll play.
I mean, I've been saying the word all night, and it's been incorrect in context. So okay, so realistically, when we go up to our three methods that we were looking at before, undetermined coefficients was going to be if we have null space. need the particular. I believe it's also called complementary, unless I got it backwards. Yeah, I'm not going to find it in here. It's in the trench book. We need the particular solution, and these are going to be easy functions, i.e. Ones that we typically see, or we can see, in the nullspace solution. So what has that been? Well, we had powers of e, basically any exponential solution. And if it isn't an exponential with e, we can also shift bases to make it exponential with e times our natural log constant stuff to juggle it around. It'll make it a little bit easier if it is in e, just because. Again, makes it nice with derivatives and all sorts of other stuff. But yeah, so typically we're going to see exponential functions in our null space solution. We're going to see polynomials or polynomials times exponentials. We're going to see potentially sine and cosine. And I mean, that's like most of the, well, that's all we pretty much get ever, but that's also pretty much the only ones that I see in our null space solutions.
Well, and honestly, these are the easy cases that people know how to analyze.
Yeah.
Everything else uses some kind of numerical method.
Also true.
I'm a friend with a researcher who actually just got his master's and is now working on a PhD, and just moved on to that PhD program. Actually, I ought to check in on him, see where he is. But he was working on a PDE, solving it, and there was just computers were everywhere. Like, he had to use computers to do all the calculations because they're so long and so involved that in some ways the only nice cases we know are the ones we've talked about with e and sine and cosine and polynomials and all that. Those are like reasonably tame for hand calculation, but in practice people will usually punt and go to a computer.
Yeah.
When you're solving a research problem, that is. Like I said, there's a friend of mine who was, for part of a research project, was using a computer to go and do all the calculation.
So to wrap up for tonight, we're going to just look at like the kinds of, or the reasons that we would use each of these things. So again, if we're going to do undetermined coefficients, we have the null space, we need the particular. These are typically going to be easy, you know, just as Zach said, stuff that you see all the time, but it's the easy case. Reduction of order is actually typically going to be, we have one null space solution and we need to find its linearly independent partner that works for whatever differential equation we have. So we're going to assume that x2 is going to be equal to some function u of t times x1. So it's going to be some function of t times our original one to get the new one. This, I believe, we did in part of the first order systems stuff that we were talking about. And it just allows you to say, okay, well, if I plug all this stuff in, now my x2 is going to get me a first order linear differential equation, and it should be solvable fairly easily. Variation of parameters is going to be one of the most powerful things that you could possibly do in ODEs. And this is going to be, again, we have the nullspace solution. And we need to find the particular. But we're going to assume, again, sort of the same as the reduction of order, that y particular is going to be equal to not a linear combination, but in this case a functional combination. I don't know if that's an actual word, but u1 times yh1 plus u2 times yh2, and this would continue if we have more of them. So u sub n y sub hn. So we're not going to assume that it is going to be a linear combination, but rather this functional combination u of t multiplied by each individual different linearly independent y that we have in the null space solution, or our homogeneous solution. Okay, so we're going to look at reduction of order and variation of parameters in how we do it in the like algebraic method next class, and that should take up a reasonable amount of time. Then we might get into some applications, but we'll see how far it goes. All right. Anybody have any questions? Alrighty. I want to thank both of my co-hosts for coming in tonight, and we'll I think I'll stick around for a little bit more mathy type stuff, and if anybody has any questions, please feel free to put them in chat, and I will get to them momentarily. Zach or Stuki, do you have anything interesting coming up?
I don't think so.
I mean, I'm getting ready for Infinite Series, so
right.
what have we got? 3 weeks, and actually tonight is the first night of 3 where we're going to be doing some review for that. So if you want to come learn some calculus stuff, do a little review of real analysis. I'm actually trying to finalize the syllabus of the stuff. I've had a lot of good things come to me for this course in the past few weeks, so I'm excited to have this all come together. But I finally figured out like the storyline, and it's very it's a little more clear than it was. So
Yeah.
I think what we're going to do tonight is we're going to do a review of calculus and try and keep us self-contained, keep this like next 3 sessions as like just a brief review of stuff. And really, we're trying to include as little analysis as possible as a requirement. You're going to be doing analysis, of course, but I'm trying to minimize the amount of stuff you have to come in knowing. So
Nice.
if you've had a Calculus 1 background, you should be fine, and we'll help you through the rest if you haven't seen a lot of this before. So I'm excited to see where this goes, and as always, anyone who's watching, come join me tonight. We'll do that about 7:30 Mountain, so in about 3.5 hours.
Alrighty.
Sounds great.
Woohoo.
Yeah.
I'm really excited to see it. I probably won't be there live, but you know.
Well, this is going to be interesting because again, it's some of this content I've taught before, but I haven't taught it this way, And so I'm going a very different direction than I did the first time. The purpose is different, it feels like. So we're going to see how it goes, and I think there are some different storylines. So I'm excited for it too. I guess the short end of it.
Nice. Alrighty. Well, I will let you two go and have fun with the rest of your night. Have fun with the rest of your couple of days here, and I'll actually get things posted this time. So.
And thank you, Stuki and Obi. Appreciate it.
Yeah, absolutely. Thank you.
Yep, definitely appreciate both of you. Thank you. Alrighty. So, now that we are concluded with class, if anybody has any questions for mathy type stuff, feel free to ask it in chat. I will take a quick 3-minute break here, cycle some water, and probably take pictures of this stuff. We'll also get rid of all the pre-roll ads and stuff like that. So, see you in 3 minutes. Be right back. Thank you so much for being here, and we'll see you in just a couple minutes here. Alrighty. Tonight is hashtag not sponsored, by Wiper and True Espresso Martini Shake. Remember, folks, don't drink and derive. Clean calculus only. Right, so let's take our pictures. Oh, so close. Okay. Let's get that one. All right, reset the canvas. And we're clean, so. Again, if anybody has any questions, please feel free. I can just drop also stuff that's in the math Discord or Penn Center's Discord or what have you. I just typically don't like to do that stuff on stream. I don't know. I feel like I'm stealing other people's content, or I probably worry too much. Right. So if anybody is curious, I not only taught differential equations, but I've also been teaching and coordinating pre-calculus class for my community college in Maryland. Sure, why not? Oi, stop moving. All right, so we, oh, right, I gotta, that's part of the problem. My mouse wheel is free rolling, so I like bumped it and it started scrolling up. Alright, so considering the following function, y equals 6x arccosine of x minus 1 at the point 1 comma 3 pi. So we want to find the equation of a tangent line. right? Y equals mx plus b. Every single time, because it is just going to be a linear function. Clearly, we want to do that. The tangent line portion of it really describes what we're doing with the slope of this particular line. And at the given point is really telling me that, you know what, I'd rather use point slope form. Right, so here we're going to say if we want the tangent, or if we want the line that's tangent to this, the slope is then going to be given by f prime at our particular point, again, x1 times x minus x1 plus y1 at the end. What do you call that thing? Okay, so what we're seeing here is that we're going to take f prime at x1. Right now we got to figure out what x prime is in the first place, or f prime is going to be in the first place. So let f of x be equal to all that stuff there. 6x arccosine of x minus 1. Alright, so f prime at x is going to be equal to 6 times, here we take the derivative of x, is just 1. So we get arc cosine of x minus 1 plus 6x times the derivative of the arc cosine, which if you don't remember what it is, like I never remember what it is, you can either go look it up, or you could say, alright, well, if y is equal to arc cosine of x, just arbitrarily using the x and y in this particular case, we could say that the cosine of y is equal to x. When you take the derivative of both sides, you end up with a negative sine of y times dy equals just dx. dy dx is therefore going to be negative 1 over sine of y, or right, arc cosine of x is x over 1. So that's going to get us our angle y, and then the opposite side there, which we need for our sine function, is going to be 1 minus x squared. So that's going to be sine of y is equal to 1 minus x squared all over 1. So negative 1 over 1 minus x squared. And I forgot the square root. Cool. Right, that's what happens when... That's what happens when you rush through things. Okay. I was looking at that, I'm like, that's tangent, what are you doing? Right, so we get this. Hey, there we go. We're having an argument in Discord. It's fine. Okay. So yeah, this is going to be our dy dx here. So that's going to go in here. So a negative 1 over square root 1 minus x squared. So this is going to cause a problem because we have, right, a 1 minus x squared. If we plug in a 1, then this is going to end up, this is going to be division by 0. So that's not good. Yeah, we were having an argument about whether there was a plus or a minus there. My hint for anybody who's in calc is go with, don't do the arccosine thing, don't memorize all these formulas. Turn it into an implicit differentiation, right? Y equals arccosine of x is the same as cosine of y equals x. That's so much easier to derive than to try and remember what the formula is or whatever else you got going on. So my recommendation, yeah, change it to something a bit nicer. Okay, so here f prime is equal to 6 arccosine of x minus 1. We could do arccosine of 0 just fine, so plugging in 1 here is not going to be a problem. But, right, plugging a 1 into here is going to be a problem. So we need to figure out how to fix that one. Okay, so then we still have to deal with the 1 minus square root 1 minus x squared there. Negative 6x over the square root of 1 minus... Oh, that is. That's an x minus 1 squared. Aha. Alright, I got tripped up on parentheses that he didn't put in. A. So that is not x squared. That is parentheses x minus 1 squared. Cool. Okay, so that's actually way better. Right, so f prime at 1 is going to be equal to 6 arccosine of 0. So at what angle do we get a 0? For cosine, this is going to get us 90 degrees. Or, because we don't want this in degrees, we want pi over 2. Alright, minus 6 times 1 divided by the square root of 1 minus, this is 0 squared. So we just get a 1. Cool. So we just get a 6 for that entire term. So f prime at 1 is equal to, this is going to be 6 times pi over 2, so 3 pi minus 6. Right, so all that can go into the bottom there. So our y value is... Nope. Back off. Alright, y is equal to parentheses 3 pi minus 6 times the quantity x minus x1 is just 1 plus y1 is 3 pi. So that's really enough. If we wanted to alter this a little bit, because we see a 3 pi in 2 different places, we could also decide that this is y equals 3 pi minus 6 parentheses x. And then we get a negative 3 pi plus 6 plus 3 pi. So that's just going to be a negative 6. Right, so again, our 3 pi here times the negative 1 is negative 3 pi, plus 3 pi there goes away, and then we... Yeah, that's supposed to be plus. Negative 6 times negative 1 gets us a plus 6. There we go. I'm glad I looked at it again. And if we want to check just what's the line going to be here, right? We want a tangent line. And then we get something that is just under 2 pi. So 6 seems to be at least reasonable. If it ends up being a little bit off, then so be it. Woohoo! Oh wow. There's a lot of people in this. There's a lot of people in here. Ooh. Alright, so we are discussing with the person in question. So a reminder here, arccosine is asking us the reverse of the cosine question. So arccosine is asking us what angle is going to get you 0 in the cosine function. So in this particular case, so we're having a misunderstanding about the fact that arccosine is not the same as multiplicative inverse. So this person said, isn't arccosine just 1 over cosine? So no, unfortunately, right? Arccosine is asking the opposite question. It's trading our inputs and outputs. All right. Right, so I think we're getting the idea of arc functions with trig. Alright, so what are we getting for slope? Alright, so let's see. Going back, what did he have before? Had the -6. I like that part. So I like that -6 part that you got. What about getting, what are you getting all together, or what's the arccosine part getting you? So hopefully this answer will be 3 pi or 3 pi minus 6. Typing. This is not going to go very quickly. Alright, we got to go to, let's see. Snag somebody else's form. Maths forum. Calculus. Linear algebra, more linear algebra. Okay, so that looks like also a good one. Let's haven't been answered on the other one yet, so all right, let's see. Well, let's take that one. Let's do this. Shoop. All right, taking the definite integral from 2 to 3 of 2x minus 3 divided by square root 4x minus x squared, all dx. So let's make sure we haven't been answered on the other one yet. Oh, we cooking. We cooking. Don't have a problem with pi over 2. It's the fact that you got something multiplied by that. Okay, so in this particular case, we've got integral from 2 to 3 of, we have some stuff on the bottom. So this is going to be x times 4 minus x. Whoop. There we go. Great. We got it. Negative 6 plus 3 pi. So we're there. Okay, we don't understand. That is my slope, but I don't understand. Because I didn't apply the same process to other problems? Not sure what you mean. Alright, so you found the slope of a tangent line to the curve at a given point, which we found was 3 pi minus 6. So what does equation of a line mean that you need? So hopefully that'll spark something there. Right here we get 2x minus 3. We could... Yep, no, F it. Keep that the way it was. And, well, I mean... 2x minus 3. In here, we get 4x minus x squared. Whoa. right? Plug it into point slope form. You got it. So the key to this is that we're doing the same problem as from Algebra 1 when we were asked to find the equation of a line and had a given slope and went through a specific point. This one is just more sophisticated. Why can't I plug arccosine of u into the derivative formula? Like right, your f prime of x is equal to this thing. Right, that's recent. That one does that. Arccosine is looking for what angle gets you the stuff on the inside. And cosine is applied to it. Okay. So if dx, if 4x minus x squared is equal to our u, then du is going to be equal to 4 minus 2x dx. What about 3 pi over 2? Okay, so great question. So we could also ask about like 17 pi over 2. So the issue is that the arccosine function needs to be a function. So there can only be one answer. Choose the domain. Right, so a function needs to map each input to, at most, one output. Alright, this needs to be a function mapping, and then this like if the arccosine of 0 is equal to plus or minus pi over 2. Yeah, when you input 1 for x, you get out 3 pi for y, and no others. Is that what we choose pi over 2? So, sort of. Natural domains and ranges for the arccosine function. Are what are we allowed to plug into a cosine function? What kinds of things are we plugging in? So I'm looking for, oh, we're plugging in angles. right? And then, like, what kinds of angles can you get? Well, it could be anywhere from negative infinity to positive infinity. Doesn't matter. You can plug in anything, right? That's what we're looking at. So we'll put that over here for a second while we go back to here. Okay. So if 4x minus x squared is u, then 4 minus 2x dx is du. Therefore, I'm going to separate this out. We're going to do, nope. From 2 to 3 of 2x over this thing. Hang on. Okay. 2x minus 4 plus 1 dx. Okay. So what we're going to do here is we're going to take this 2x minus 4 bit and we're going to transform it into negative 2x plus 4. That's super easy. All we need to do is take out a negative. Then we're going to deal with this plus 1 bit on its own. So we get integral from 2 to 3 of negative parentheses, whatever, 4 minus 2x dx, all over square root 4x minus x squared. I have no idea what this music is. Okay, plus we have a 1 dx integral from 2 to 3 divided by, same thing, square root. But this time, what I'm going to do is I'm going to make this a difference of square. No, I'm going to do completing the square. So completing the square. Right, so blank plus 4x minus x squared is equal to something squared. So it's going to be minus x. This is going to be a 2 minus x. And then a negative outside. Okay, so if we're looking just at the cosine function, I would say, is there going to be any sort of restriction for just like standard cosine function? The hell? That was weird. Alright, so this is going to be a negative 4. Right? Negative 4. Negative 4x, but a negative from the outside makes it positive 4x, and then a positive x squared. Okay, we're going to restrict the domain artificially because we need to make the cosine function 1-to-1. Okay, so we're doing completing the square. So here this is going to be negative parentheses 2 minus x all squared. Could be x minus 2, it really doesn't matter at this point. But either way, right? It's going to be a negative on the outside anyway. Parentheses 2 minus x parentheses squared. Alright, but in order to make that happen, we had to subtract a 4 on the inside, which means we had to add a 4 on the outside. Alright, so this thing is periodic, so therefore it comes back eventually, right? Which means that can't be 1-to-1 and can't have a functional inverse. Alright, so now I gotta deal with that. Alright, so the first one is not that bad. This is just a U substitution. It's fine. Right, so this is going to be negative integral from 2 to 3 of du over u to the 1/2. Plus right, again, this u and du is going in here, then goes to here. Right, now this thing. Roro Sugimoto, how are you? I am not familiar with signals analysis, and nor am I familiar with the EULA parameterization, but I can at least take a short look at it and see if it makes any sense to me whatsoever. Control theory, etc. Describe the best three increasingly types, general kinds of plant. Stable CISO plant. Let P of S be transfer function of stable single input, single output system. Okay. Let omega be a set of stable and proper functions of S. Then the set of all proper stabilizing controllers for the plant P of S can be defined as the following. Q is arbitrary, proper, and stable function of S. Q of S parameterizes all stabilizing controllers. Yeah. I can't say that I'm familiar with anything in this. Nice. Consider a general plant with transfer function P of S. Further, the transfer function can be factorized as N of S over M of S. M and N are stable and proper functions of S. Right. Yeah. No, this is getting too deep for me, unfortunately. Unit parameterization. Example. Oof. PDF. Automatic download, man, come on. Good news is that this is a differential equation, and I am fairly familiar with differential equations. No, don't do that. Come on. Symbols. We need belongs to. Where is our little set theory? There we go. Belongs to. Cool. No. No. Dynamic output feedback controller. U is equal to KY, where K is state space realization, given below. Fun times. Alright. Got it now. Got this problem on the run. Yeah, no, this is gonna be no problem. But hey, you need help with differential equations. Whew. Goodness. This is the only output for cosine. Which matches the cosine ratio value of 0. Oh yeah, yep. Pretty much like straight math right up the list. Calc 1, 2, and 3, and some of the higher level undergraduate, maybe graduate classes. So it depends on what you got. But definitely. I also tend to teach in a way that's very like conceptual. So trying to make sure you get the, yep, so Calc 3, yep. Whew.
I don't ever slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up.
don't ever slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up and make a statement. I don't ever slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up and make a statement.
Everything I do so instinctive and so passionate. Every word I move so descriptive like an adjective. I got a vendetta against people who patented being negative when you should be getting after it. I got facts over tracks, this and that. Spitting slow, spitting fast. I could roast, I could gas. Think I'm okay at last, but I don't know if that can erase all the past. And the pettiness, a reflection of the emptiness. Hilarious, you think you're worth my time, you're delirious. Mysterious, because you hide behind a fake exterior. Inferior, you know I'll always be a bit superior. Get off of me, this ain't no humble brag. I want you to hear words, you can say them back. I want you to feel free from the chains at last, and to believe in what you got, it was built to last, yeah.
Now that I've been put through hell, I never got anyone's help. I had to do it all myself.
I don't ever slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up and make a statement. I don't ever slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up and make a statement.
Gonna learn the consequence of being incompetent. Mental health is confidence, dreams and some honestness. I'm not here to save the day, that's for you to take away. I could play a million mind games, but instead I say something not illogical, something that is topical. Rub it on and watch it go, make yourself unstoppable. Dreams are irresponsible, but they're always possible. If you just believe, you could be so remarkable.
Thoughts in my head, a collage and they spread. I'll be great one day, going off of my meds. No, I'm not giving up, no, I'm not giving in. I will make it to the top, taking off in the wind. I gotta make it, I'm saving every day to taste it. I'm patient, but my mind, it can hardly take it. I'm chasing a dream that I've had for several ages. A vacant, modern kingdom for the taking.
Now that I've been put through hell, I never got anyone's help. I had to do it all myself.
I don't ever slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up and make a statement. I don't ever slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up and make a statement.
I don't ever slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up.
Makes that positive, and that's squared. So negative does not come in yet. So 4 sine squared theta. Then that's going to make 4 times the quantity 1 minus sine squared theta. So that's going to be cosine squared theta. Okay, cool. Negative 2 cosine theta d theta over 4 factors out becomes 2 on the outside of the square root. Square root of 1 minus sine squared theta is cosine squared theta. Then that whole thing is going to cancel out, divide out with cosine of theta. So therefore we have a -1 negative integral of d theta, which is negative theta when x goes from 2 to 3. Which means a negative right, let's not do theta. Theta is inverse sine of (2 minus x over 2). Taken from 2 to 3. Alright, x is equal to that. Cool. It's going to be a negative inverse sine, oops, sorry, of 2 minus 3 over 2 minus, which means plus, inverse sine of 2 minus 2 over 2, which is 0. Alright, this is all going to be negative 1/2. This is going to be a negative pi over 6 plus inverse sine of 0 is 0. So I'm getting a negative pi over 6. Did I take any shortcuts? Did I factor anything out? Doesn't look like it. Okay, cool. And then this one is going to be a negative integral of 1 over u, that's u to the negative 1/2, is going to be a u to the positive 1/2 multiplied by 1 over a positive 1/2. So that's going to be a negative 2 times u to the positive 1/2 power, evaluated when x goes from 2 to 3. So again, change variables back. Our u was equal to the 4x minus x squared. So negative 2 square root of 4x minus x squared. Taken from 2 to 3 minus pi over 6. Alright, negative 2 times quantity, because this is a linear operation, so we can just do the 3 and the 2 separately as two things, and then worry about the negative 2 and the other stuff after. So this is going to be a 12 minus 3 squared is 9, so root 3, right, minus square root of 8 minus 4 is 4, which is 2. Cool. Negative 2 root 3 plus, again, this is a 4, square root is 2, times 2 is 4, minus pi over 6. That appears to be what we've got here. So, let's go back to Discord and tell whoever it is that, hey, this is what I got. Hmm. All right. Oi! What's all this then? This was working on a Calc 2 type problem for somebody that was in this was Penn Center's chat. Not chat. Discord, but then I just noticed that it was from the 9th. So I think they're probably a bit past time on that one.
I don't ever slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up.
I don't ever slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up and make a statement. I don't ever slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up and make a statement.
Everything I do so instinctive and so passionate. Every word I move so descriptive like an adjective. I got a vendetta against people who patented being negative when you should be getting after it. I got facts over tracks, this and that. Spitting slow, spitting fast, I could roast, I could gas. Think I'm okay at last, but I don't know if that can erase all the past. And the pettiness, a reflection of the emptiness. Hilarious, you think you're worth my time, you're delirious. Mysterious, because you hide behind a fake exterior. Inferior, you know I'll always be a bit superior. Get off of me, this ain't no humble brag. I want you to hear words, you can say them back. I want you to feel free from the chains at last, and to believe in what you got, it was built to last, yeah.
Now that I've been put through hell, I never got anyone's help. I had to do it all myself.
I don't ever slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up and make a statement. I don't ever slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up and make a statement.
Gonna learn the consequence of being incompetent. Mental health is confidence, dreams and some honestness. I'm not here to save the day, that's for you to take away. I could play a million mind games, but instead I say something not illogical, something that is topical. Rub it on and watch it go, make yourself unstoppable. Dreams are irresponsible, but they're always possible. If you just believe, you could be so remarkable.
Thoughts in my head, a collage and they spread. I'll be great one day, going off of my meds. No, I'm not giving up, no, I'm not giving in. I will make it to the top, taking off in the wind. I gotta make it, I'm saving every day to taste it. I'm patient, but my mind, it can hardly take it. I'm chasing a dream that I've had for several ages. A vacant, modern kingdom for the taking.
Now that I've been put through hell, I never got anyone's help. I had to do it all myself.
I don't ever slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up and make a statement. I don't ever slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up and make a statement.
I don't ever slow up, no I don't take shit. I got no love for the fakeness. If you wanna play tough and wanna hate this, I'll always show up.
Fisherman's flat cap. Alright, cue Sensation, who's going to make fun of me. I got it, and it was like, it was the one that like slipped over the back of my head, and I was like, ooh, that's perfect. And it fit just so nice. The rest of them, I put it on, it was like pinching at the corners of the temples and things like that, and I'm like, that's just not right. But like, if it was, I would probably want, if I could, to get like a darker fabric instead of super light green. It's just, seems a little weird, but at the same time I was like, well, don't know if I want to, you know, order in custom or whatever. And it was surprisingly inexpensive. Like, the two of us, me and my son, who is only 8, but still, we walked out of there with 2 caps for like 60 pounds. I mean, it was really cheap compared to what I was expecting. Alright, we popped into another one here. We'll leave the watermark on, I suppose. Nope, not that. Not that one. That one. Right, so somebody posted this in the math Discord, you know, math homework, whatever. So, so his initial question was, I don't really understand how to do any of this, but this is going to be your pre-calculus coming back to haunt you / support you. So if f of x is equal to this stuff, then f of x plus h, which is, again, this right here, is going to be equal to 3 times the quantity x plus h squared plus 4 times the quantity x plus h plus 1. Which is then 3 times the quantity x squared plus 2hx plus h squared plus 4x plus 4h plus 1. And so that's going to be 3x squared plus 6hx plus 3h squared plus 4x plus 4h plus 1. Right, f of x plus h. Then, if we want to take the entire limit there, limit as h goes to 0, that is really, oh dear. Limit as h approaches 0 of all that stuff. So 3x squared plus 6x 4hx plus 3h squared plus 4x plus 4h. Oh dear. 4h plus 1 minus parentheses f of x in the first place, which is 3x squared plus 4x plus 1, and divide all of that by h. So I'm going to take the limit as h approaches 0 of 1 over h times the quantity, and here we get a 3x squared and a negative 3x squared, a 4x and a negative 4x, and a plus 1 and a minus 1. So all of those pieces are gone, and we're left with 6hx plus 3h squared plus 4h. That is all that is left. And when we take the limit as h approaches 0, multiply through by 1 over h, and we're left with 6x plus 3h plus 4. When we take h goes to 0, this eliminates our middle term, and we just get 6x plus 4. The added benefit of this is that the derivative ddx of 3x squared plus 4x plus 1 is going to in fact be, again here, 3 times 2x plus 4 plus 0. So 6x plus 4. So this limiting process where h is going to 0 is equivalent to taking the derivative of the original function, whatever it is. This especially gets fun when you start looking at really weird functions. So the function 2 over x is not that bad. Here, in this case, this is going to be 2 over x plus h minus 2 over x all over h, and again, limit as h approaches 0 is going to end up being a limit h approaches 0. Hey, Liz! Oh, I just went downstairs and got this. I haven't had it at all, but yeah, my son and I had to go and get a Yorkshireman's proper cap, but yeah, I was remarking that it was rather incredibly inexpensive to get like a couple of these, because I got one and my son got one. Granted, he's 8, and the lady was like, I don't know, do you want like the 8-panel one? Because it's got 8 panels that come up to the center. They're all sewed along the thing, so it's got like a button in the middle and then 8 sections. And he was just like, no, flat cap. Have to get a Yorkshire flat cap. Like, okay, so this thing we're going to multiply by both x and x plus h, top and bottom, which is going to get us 2x minus 2 parentheses x plus h all over h. Oh. H times x times x plus h. All right, when we do that, Numerator becomes 2x minus 2x is 0, and a negative 2h. All divided by h, which then divides out one of those h's, x times x plus h. And that's a limit as h goes to 0. And that's going to be a negative 2 divided by x times x plus 0. So a negative 2 over x squared. Woo! Yeah, I haven't shown this off. But my son was all for it. He was like, we have to get Yorkshire flat caps. And I was like, well, I agree. Let's see. So an interesting thing starts happening when you start talking about like other types of functions. Sine is one that typically people will work on with this, and it's I prefer to know your sum and difference formulas because you're going to need it for this. And then there's going to be also multiple. It's going to be multiple. Yep. All right, there's going to be multiple functions which require like special knowledge of stuff. So one of them is like 2 to the x. This is going to be 2 to the x times 2 to the h minus 2 to the x all over h is going to equal to limit h goes to 0 of 2 to the h minus 1 over h multiplied by 2 to the x. So like this part you have to know what this is doing. Are 2 to the h minus 1 all divided by h, right? Obviously as h goes to 0, this is going to approach 1 minus 1 over 0 or 0 over 0. So it's indeterminate. But like in terms of what that's actually going to become, creates a small problem. Now the interesting thing about it is if we were to like mess around with just getting a numerical solution, this ends up being not 1, not 0, not infinity, but a special other number, which, you know, for anybody who's done this before, it becomes pretty obvious what it is. But I can't remember exactly how to... There's a way to get like a good solution out of it. No, I can't remember what it is. I'm kind of curious if we can make this work. Sorry, limit as, let's call it C goes to 1 of let h be equal to log base 2 of c. This is going to be 2 to the log base 2 of c. This is probably not correct, but natural log of 2 multiplied by c minus 1 all over natural log of c. Anybody know a way out of this infinite loop? Alright, let's see. So I mean, at this point, right, it should be that c minus 1 over natural log of c goes to 1. Works by L'Hopital's, but I'm trying not to use it. It's kind of funny. I know a Jonathan Boyle. Sorry, the music here, "Steam Train Sweethearts" by Jonathan Boyle. I know a Jonathan Boyle, so. It would surprise me greatly if this was him. C approaches 1 of c minus 1 over natural log c. Again, this needs to be 1 times natural log 2 times 2 to the x. Worry about that. Just in case anybody is out there, my name is Obi-Wan Pez, and this is Simplex Pachinko. We have been doing some math tonight. We do differential equations on Monday and Wednesday nights. I am running a class on differential equations. My two co-hosts so far have been enstucky and Stucky, and e to the 2i pi, or Zach, and we are just going through and having a discussion about like differential equations, how it works, and how to like logically kind of underpin the entire subject and try to get interesting ways of teaching and learning the subject and things like that. So we are currently starting on second order differential equations and getting all of those interesting methods that we have learned from the first order systems now applied back to second order algebraic differential equations. Yeah, Real 200, I don't know what that's about. Don't think I've heard that one. Unless there's some sort of pun. I mean, I've looked up some stuff, but obviously not the right one. I'm trying to figure out how we can make this one go to 1 nicely. Take the limit as c goes to 1 of c minus 1 over natural log of c. Okay. I think probably we are going to read out to somebody who's on. Right. Maybe I should also first try the actual command that somebody was so nice to plug in. Enigma. Damn it. Alejandro and High Potential are the only two currently on. No, don't do that. Don't do that. Back to Twitch. Okay. Ooh. Rogan is playing Chance of Senar. I think we're going to have to go raid Rogan just for that, because it is quite an amazing game. Those of you who have never played Chance of Senar before, maybe you want to try. But yeah, it is a brilliant, somewhat minimalist, yeah, that's not entirely true, but it is a language game. I am a big fan of language games, and so I'm going to run over there. And if anybody is interested in following on over, Rogan is a librarian who does archival work at the at Virginia Tech University, and he's just a really great guy. And he is also wearing a Yorkshire flat cap. So I mean, clearly, obviously, that's just the way we gotta do this. So I hope everybody has a good night. We'll be back tomorrow night, at least I'm planning, for general math help. We'll probably run over there and Yeah, we'll probably do some stuff. I don't know. We'll figure it out. And then we'll be back on Wednesday for more differential equations. So thanks everybody for stopping in. We're going to head on over to Rogan27, and hope you follow. Have a good day. See you all later. My name is Obi-Wan Pez, and this is N Simplex Pachinko. Have a good night.